want, let's say, to describe atmosphere consisting of such gases, then the configuration manifold for the whole media M will be the total space of this bundle, with fibers diffeomorphic to projective plane for homonuclear gases and two-dimensional sphere for heteronuclear. Another interesting example is water. This example delivers us the configuration space of particle which is diffeomorphic to projective space. Well, I will not go into details how this happens to be true. All the references are in our preprint. Now, another example that are interesting for us is a medium composed with solids. It is a so-called Cassera theory. It was proposed by two brothers, Cassera brothers, in the beginning of 20th century. They considered media composed with solids. Solids also and rods. In this case, configuration space of such medium is this. So the fiber is diffeomorphic to SO3. All these examples give us motivation for the following definition of a medium with inner structure that we will use in this work. Namely by a configuration space of such medium, we mean the following. First condition, that we have a small bundle pi, where M and B are Riemannian manifolds equipped with matrix GM and GB. Then the second condition, that we need that we can compare inner structures, that is fibers of pi, at different points of B. We assume that this bundle is equipped with a connection nabla pi. Well, and this connection splits tangent space into vertical and horizontal paths, and the restriction of the metric G on H must coincide with GB. The third condition that must be met is that the flow in the medium is given by a pi projectable vector field X, and this it means that field X preserves the bundle pi. The field, this field can be split due to the connection nabla into the sum, where XV is the vertical field and XH is a horizontal lift of the vector field pi star X. So this is our what we mean by configuration space and what kind of conditions we want to be true for vector field X. Now a few words, not a few. Now some words about the thermodynamics of such a media with inner structures. We use The thermodynamics in our model is based on measurement and its role in thermodynamics. More on that a bit later. In our model, we have two extensive quantities: the internal energy density epsilon and the rate of deformation delta, where delta is the covariant differential of flow velocity field X, and nabla is the Levi-Civita connection associated with the metric Gm. The corresponding to these quantities are the intensive quantities, and they are temperature and the stress tensor sigma, temperature theta and stress tensor sigma. In this work, we use the duality of NT and NT star, which is given by this pairing, and sometimes we use NT and NT star interchangeably. Therefore, the thermodynamic phase space of the medium is phi, which is R3 times NT star times NT, with coordinates S, theta, epsilon, sigma, and delta, where S is the entropy density. The phase space phi is a contact manifold equipped with the structure form alpha. This. More details on this topic may be found in lectures. I'll give the reference in the end. In the lectures on measurement in thermodynamics. I will not go into details here. These details indeed may be found in this lecture, so we just use all the constructions from there. It's just a brief enumeration of facts we need. The first law of thermodynamics means in this situation that the thermodynamic state is a maximal integral manifold of the differential form alpha. That is, it's a Legendrian manifold L of this dimension. Because the density of entropy, I mean, because we don't want entropy to be involved in our conservation laws later, which govern motion of the medium. Now we want to eliminate it from our geometrical description of the thermodynamics. And for this, we can consider the projection small phi from of the contact manifold phi to the symplectic manifold phi tilde with the structure form d alpha. The restriction of this mapping phi to the Legendrian manifold is a Lagrangian manifold in
I'm sorry, one question. When you say that you consider the condition of Legendre manifold be exact, it corresponds physically to the condition that entropy is not increasing, yes or no?
Oh,
Or no, because usually
I don't know.
No, this physical meaning, geometrical meaning of the condition, the Legendre manifold, it means that entropy, the process is quasi something, some condition.
Yes,
Yes. Okay.
Yes,
Okay.
yes, it's some kind of quasi-static
Yes.
process.
Thank you very much. I think it's all right.
Yes. Oh, I'm sorry. Where did I stop? The restriction of the mapping phi to the Legendre manifold L is a Lagrangian manifold in a symplectic manifold which is equipped with this structure form. I said it already. Okay. Now we may reformulate the first law of thermodynamics by saying that the thermodynamic state is a Lagrangian submanifold of the symplectic manifold phi tilde with a structure form d alpha. So instead of Legendrian manifold, now we consider Lagrangian submanifold. And if we are given a Lagrangian manifold L tilde, the corresponding Legendrian manifold may be reconstructed up to the translation along the s-axis. It means that entropy as a function is defined up to some constant. And also, very important requirement is that the following quadratic differential form kappa is negative definite. So again, I want to say that all the details may be found in the lectures. The meaning of this form is the following. The submanifold where the quadratic form is degenerated divides our Lagrangian manifold into domains where kappa is negative definite or positive definite. And the domains where kappa is negative definite, well, these domains correspond to different phases of the medium. By phases, I mean gas, liquid, gas or liquid. And all other domains are domains where the thermodynamic state, well, is unstable. Given that we have a symplectic structure on the space phi tilde, we may define well, this structure defines the following Poisson bracket. And why do we need it? Because we may want to define thermodynamic state of the medium not in pure geometrical way by some Lagrangian manifold, but by some equation of states, the relations between thermodynamic variables. And this to be and if we want that these equations indeed define a Lagrangian manifold, all their pairwise brackets must vanish on this system.
Sergey, can I ask you?
Yes.
So first of all, about quadratic form. This quadratic form on the big symplectic manifold, it has split signature, right? So you talk about negative definite on Lagrangian manifold.
On
right?
Lagrangian manifold.
Yes. So because it's neutral signature, but when you restrict, you talk about
Yes,
this, right?
yes.
Okay, that's clear. And the next formula for bracket, there's lots of typos probably because it has to be bilinear in FG, right? And there's GG, many places, which makes it quadratic in G, but has to be linear in G, right?
Indeed.
Yeah, it's correct. It's misprints. It should be couple F and G in each place.
Indeed, yes. Thank you. Thank you for this remark. Yes. Some of the G's are F's. I believe this is F.
Yeah.
And this is F.
No, this, yeah.
This F.
Это sigma.
And the rest.
Mm.
And yes. Thank you. Thank you. Well, it will be convenient for us to introduce the density of Helmholtz free energy H on manifold L. Why it is convenient? Because it removes entropy from the description of the thermodynamic states. Instead of entropy, we have only temperature theta and deformation tensor delta. And yes, and in this case, for the equations the equations which define Lagrangian manifold L tilde are the following. And we also may write this quadratic form kappa in these coordinates, and it has the following form. Now we I want to discuss how to what type of these equations of state we may expect. What I mean, if we consider that a medium possesses some kind of symmetry, which is given by some algebraic group G, then this action of this group may be prolonged on the thermodynamic phase space phi if we assume that the action on thermodynamic variables as theta and epsilon are trivial, and it is natural on product nt times and t star times nt. Why do we need this? Because if the the medium has some type of symmetry, some kind of symmetry, then it is natural to expect that the thermodynamic state has the same symmetry, and it means that its thermodynamic equations of thermodynamic state must be expressed in terms of such invariance, and not in terms of just tensor delta or sigma, but in terms of its invariance. So let J and so on J1 be a set of algebraically independent G invariants on phi, which generate the field of all rational G invariants. Then a regular thermodynamic state. What does it mean? That it is J-invariant algebraic Legendrian manifold L may be written in the form H is a function of this invariance, where H is a rational function. So it's almost that I said before, that we want to equation of state depend on invariance of this group, not on just tensor delta. Well, here we in present work we consider only Newtonian media, that is a media which possesses a symmetry group OG, that is orthogonal group where T is a Euclidean vector space. No, well, its role it is a tangent space to manifold to our manifold M, which equipped with a metric G. To construct this rational invariance, we use the following theorem proved by Procesi. This theorem states the following: that the algebra of polynomial OJ invariance of linear operators is generated by this Artin-Procesi invariance. Here A is the operator and A prime is the adjoint operator to A with respect to the metric G. Yes. And the theorem we actually need is the following, and it follows that from this Procesi theorem, the Rosenlich theorem, and the observation that codimension of regular orbits equals n times n times n plus 1 divided by 2. We have this theorem that all rational invariance of OJ action on linear operators are generated by any algebraically new algebraically independent Artin-Procesi invariance. And we may recall that the Helmholtz free energy H for the Newtonian media is it must be an OJ invariant function because the action of OJ is trivial on thermodynamics variables like entropy, epsilon, and entropy, energy, and temperature. And therefore, function H, which defines this Helmholtz energy, is I'm sorry, is rational. I forgot to write something. Yes, I forgot to write on slide. Well, and in this case, I mean by this I mean that we have H as the function of temperature and this Artin-Procesi invariance, which is rational on them. We have the following state equations. So sigma is tensor sigma is a derivative H by theta, by delta, and it is the sum. It has the following form. I will not go into details how we differentiate by functions by tensors. It's it's not important for now. So what we are really interested in now is that we may define the Helmholtz energy in some way and obtain all other equations of states. The first natural case is the media that satisfy Hooke's law. It means that Helmholtz free energy is a quadratic function of delta, and therefore it has the following form. So these are Artin-Prochet invariants. This corresponds to the to the trace of operator delta. This corresponds to the trace of product delta and delta prime, and this is just a trace of delta squared. So, and A, B, C, and D are some functions, and we may see that this function is indeed a quadratic function on delta, on the formation tensor delta. And in this case, applying this formula, we indeed obtain the expression for stress tensor delta. Well, this expression may seem well known because it's what we may see in Navier-Stokes equations. Their A, B functions A, B, and C are viscosities, called viscosities, and D plays or minus D plays the role of the pressure. But what's interesting is that usually the cases when the operator delta is self-adjoint, only these cases are considered. And in this case, we, of course, have only two viscosities. In this case, it will be A plus B and C. The next thing we want to discuss is its thermodynamic invariance of Newtonian media with inner structures. In this case, the construction of invariants are almost the same. We use the very same Artin-Prochet invariants, not the same, but very similar. So let a Euclidean vector space T with metric G be the sum of a vertical space V and horizontal space vector space H. And we should study invariance of the action of this action on operators on this space, on the space T. What it means that we have two groups. Well, on the base that is V, we have action of this group, and on the space H, we have the action of this group, and they, well, acts well, each group only acts on its space, on the corresponding space. So both base and fibers have some kind of symmetry, and we want to discuss and we want to find all invariants of this action. as I said before, we again use Artin-Procesi theorem, which delivers us algebra of polynomial invariants of this action on operators. And again, as before, all rational invariants of this action are generated by independent polynomial invariants, by independent polynomial Artin-Procesi invariants. Now, I didn't write the formula for how much we should expect, but it is not. It's not just the sum of invariants of this action on space V and of this action of space H. It has some invariants composed of both spaces. Well, let's look at an example. So similarly to the ordinary Newtonian media, by ordinary we mean that they do not have any inner structure. We have the following equation of state, and if we again assume that this media satisfy some kind of Hooke's law, that is the Helmholtz free energy is a quadratic function of the deformation tensor. It in this case H will be this. So now we have not three. Now we have six so-called viscosities and two B1 and B2, well, equivalents of pressure. We have one pressure on the base and one pressure in the fiber. And again, by applying this formula, we may find the form of stress tensor sigma. Now, when we constructed all, in some sense, constructed all thermodynamic states that we need, we discuss conservation laws of motion. By laws of conservation, I mean the conservation of mass, of momentum, and of energy. Well, generally, these equations may be written for an arbitrary Riemannian manifold, and the many difference between this situation and our situation is that we have inner structure and we must pose some restrictions, some conditions on the flow velocity field and on the thermodynamics. Well, so in this section, in this part, we consider a Riemannian manifold M with metric G. We assume that this manifold is an oriented manifold, and omega is the volume form associated with metric. And, we denote nabla and d-nabla, and we denote by nabla and d-nabla the Levi-Ciuta connection and the covariant differential associated with metric G. And by d over d2, we denote the material derivative. The next thing we need is to construct some kind of generalization of the divergence operator of vector fields and of linear operators. So the divergence of a vector field may be defined in the standard way through the Lie derivative. But on the other hand, if we consider the covariant differential of x, d double x, that is a field, that is a linear operator on T, we get that divergence of x is exactly the trace of this operator. We may see that these constructions are equivalent by writing down them in local coordinates. Yeah, this is the expression for d double x in coordinates. So we just
Differential.
Well, this this construction is pretty well, it's known, but this observation may help us in the important case, which is for us the case of linear operators. Because in the conservation law of momentum, we will need to use divergence of the stress tensor. And we define the divergence of the operator in the following way. We consider covariant differential of the operator and taking contraction of the first and third indices, we get a differential form that we call the divergence of operator A. And in local coordinates, we have the following expression for this divergence. Something wrong. Oh, okay. Now a few words about how we deal with the momentum conservation law, in particular with its right-hand side. We consider the stress tensor sigma as the surface force applied to some an imaginary surface of some small volume, and at each point this this force is orthogonal to a normal vector to this surface. Normally, we will find the integral sum of these forces, and thus we obtain the resulting force on this volume. But unfortunately, in this case, we cannot do this because each of these applied forces, well, they belong to different spaces. So I will not go into details because they are pretty long and calculation heavy, but it can be indeed shown that the density of internal force, that is the resulting force on the small volume, is indeed equals divergence of this tensor. And once again, we write NT here using isomorphism between NT and T star. Now conservation. Now we talk a little bit about on conservation of conservation laws. So the first law we write is the conservation of mass. It is written in the well, usual way, and idea behind this equation is that amount of medium contained in an elementary volume, that is rho times omega g is conserved along the flow of vector field x, and it's equivalent to this equation. The second equation is well, it is written in a standard way as a second Newton law. Here, density plays the role of mass. This is the acceleration, and divergence sigma with flat sign is the force. Flat sign means isomer vector dual to the form divergence, because divergence of sigma is a form, and divergence with flat sign is a vector field. The third equation is also written in pretty standard terms. Here, epsilon is the internal energy density, and JQ is the vector of heat flow, and usually it is given by Fourier's law. These terms describe the mechanical energy of change of mechanical energy. Well, in work of the internal forces while the media is in motion, and these equations three are not complete without the thermodynamic equations, which are given in this form. So if we define H in some form, we complete this system by these equations of thermodynamic state. And yes, and the last condition we need, that is the flow velocity field X must be a pi projectable vector field. Well, it follows from the first three conditions which we imposed in the beginning when we described our model of the medium with inner structures. That is all. I don't know, was I too fast or too slow, but that is all. And these are some references we used. These are lectures on thermodynamics and measurement. This Rosenek theorem we use, that these are Processi work on these invariants, which were extremely helpful for us, because they indeed give us the way to write down the thermodynamic state we need. And the fourth one is the reference to our preprint for this study. Well, thank you.
Thank you, Sergey. Let us thank the speaker. And if anyone has questions, you're welcome. Please.
Can I ask a question, please?
Yes, of course.
Yes. So Boris Kruglikov. So that's a question about Processi. So well, actually two questions. So first of all, why is it Processi? Because I kind of used to think that invariants are obtained through traces. That's more or less Weil theory, right? Classical invariants of Weil. So maybe Processi goes a bit like deeper, specializing number of those contractions that you need, or like he maybe even go to describing syzygies. So, but Yeah, can you maybe comment what the difference between Procesi and
Can I
wild?
comment your question?
Yeah.
It's really not wild. It was Arkin hypothesis that invariance generated by traces.
No, wild was earlier. While is standard reference, and he was definitely earlier.
But it was hypothesis, Arkin hypothesis, and Procesi proved the hypothesis. So it's not elementary statement.
Well, as far as I can see,
it doesn't follow directly from what you mean by wild. It's not wild really. It's so-called first fundamental theorem in GL invariance, but it's not so straightforward. It's very long. It's a very long paper of Procesi.
What's the difference? So wild states that all invariants obtained by traces.
No.
Yes, a contraction.
It's not question about one operator. It's question about some set of operators. And this is really Procesi result. So certainly for one operator, it's just trivial. It's student level theorem.
No, not about one.
It's a set of operators. It's not so easy.
Of course, for set of operators, yes. So that standard result used like in general relativity that all obtained by traces and they are attributed to wild. That's more or less standard references.
No, Boris, you're wrong. It's very deep result of Procesi.
So you say that it's a result of 2005 and before it was not known.
No, 2005.
No. It's a book.
It's a book.
It's a book.
Published not in book. It was published. It was special paper.
But what is the reference to paper? Which year?
I don't remember now.
I mean, it was used like from 60s. Definitely, like if you subtract even 40 years, it will not be enough. Okay, it's historical question. I don't want to go deeply in
no, it's mathematical question. It's very deep result of Procesi. I'm sorry.
But then you probably have to say what's the difference with wild theorem. Okay, I don't understand the difference. I made some search and I see that Procesi actually is used like he described in certain cases syzygies. Yes, I understand that the step
No,
forward.
It's not Procesi. It's a Russian mathematician found this syzygies. Procesi proved exactly what he proved. He simply gave generators an algebra of invariance.
So wild theorem discusses not only actually the endomorphism, but actually for all tensors. So the endomorphism is just one tensors, and the invariance of those, that's actually
and this is tuples of operators. It's different from one operator, from one tensor. It's just some tuple of tensors, and it's believe me, it's not so elementary.
Okay, second question. How do we actually use it? So I see you formulated, but I mean, I kind of missed. Maybe you can just
yes.
Tell me in which sense you actually use it. Where are those huge contractions?
No huge contractions, because what you can see on this page that we use only as a quadratic function. So actually what we need here is only square, trace of square of trace, and trace of the product operator and its adjoint. So, well, we didn't use these long expressions. What we used is actually these two terms.
And alpha 1 plus alpha 2 less or equals than 2, right? Alpha 1 plus beta 1.
Alpha 1, yes.
So
yes.
Yeah, okay.
So we need only second order invariance.
That's definitely a much simpler result. That those are invariants which are obtained by linear and quadratic expressions.
Well, it's easy to guess, but it's not easy to prove. That all quadratic polynomials invariant will be of this form. It's not easy to see without Procesi.
Okay. Yes, that's all my questions.
Well, any more questions?
Maybe one more. So are there actually syzygies already for those quadratic invariants?
Oh,
There
no.
should be.
I don't
No.
know.
No, these are
Only in dimension 2.
Okay. Yeah. So these are like free algebra. Well, generate.
Oh, no.
Generate. There's no syzygies, you say, right? So they generate free subalgebra.
No, it's not algebra at all. It's just simply invariance of second degree. It's not algebra. It's just only invariance of second degree.
But if you start generating from them algebra, they will be syzygy, right?
No.
So it's free subalgebra.
No. It is to get all invariants, you need all the stuff that Sergey just wrote, the long traces.
Right, but you take those invariants which are quadratic and you generate subalgebra into the algebra of invariants, yes?
Oh.
That's the question, is it free or not?
Certainly not.
So then there are syzygies.
Yeah, but not between second, there will be syzygies, but in higher degrees.
But still, it's restriction, so therefore the invariants are not independent.
Okay, but I don't understand your question. So what
can you use like those guys as invariants? That's another formulation of my question, right?
What?
Can you use this expression like as invariants? If they are independent, you can use them. But if there are syzygies, you can't.
No, as a second degree invariants, they are independent. But as a simply invariants, possibly there are some relations, but it will be relations of higher degree.
Okay, thank you.
So as polynomials of second order, they're independent. But if you consider
yes, with real coefficient, real coefficient, yes, of course. Yes, I ask about of syzygies inside the algebra of invariants.
Oh yeah, possibly there are some syzygies. But I don't think they will syzygy between these invariants. They're more complicated. They generated this Hamilton-Kelly expression for invariance. It's very similar to the standard case. But anyway, it's just has much higher degree than in dimension 2. It's true, but in high dimensions it's the higher order syzygies.
Well, any more comments and questions are there? Well, if no, let us thank the speaker again. And thanks everyone.